So today we're going to talk about recursion. I know some of you kind of already know what recursion is. You've implemented some of your challenges in using recursion. But before we actually get into recursion, we're going to talk about something called the call stack. Has anybody heard of the call stack, execution stack, or anything? Yeah, it's just really, it's still hard like for me to like even conceptualize. It's essentially well, let's just jump into it.
There's a YouTube video for computer file.
Okay. For the call stack or recursion? Okay. Yeah. So what is the call stack? Does anybody know what a stack is?
It's like towers. You stack up cubes or towers. So pretty much the same thing.
Yeah, a stack is it's a type of data structure that just like a queue is like a queue, and then there's a stack. A stack is a type of data structure that operates last in, first out. So think of when you're making pancakes. You make a pancake, you put it on your plate. You make another pancake, you put that pancake on top of the old pancake, and it stacks up. And then when you take them off, the order in which you eat them, you take off the top, you eat that one, take up the top. So it's the last one that comes in is the first one to come out. LIFO, like last in, first out. It's an acronym. If you've been in accounting or finance.
Or any job.
Or any job. Yeah, there we go.
So the call stack is exactly like the queue, except for last in, first out, versus the queue is first in, first out.
Yep. Except the call stack essentially stores the order. It stores executions of code in the order they are executed and removes them when they're done executing. So a function starts executing, it gets put on the stack. And then if that function calls another function, it gets put on top of that function. And then when the top function stops executing, it gets taken off the stack. And then when the next one, when that one's done executing, it gets taken off the stack. So we're going to get into this more with recursion based off of how recursion operates. So, but first, we're going to cover the call stack. So on the right-hand side, we have this is like a call stack visualization. We have a main function followed by a second function and a third function. So, and then down here in this file, main is actually executed. So when main is executed, it should be put on the call stack. And then this console.log, console is a function. So the console.log should get put on the stack as well. And then the second function is invoked. So then the second function, then the call stack, the console.log is done executing. So the console.log, it just executes and finishes right away. So then that console.log starting gets removed from the stack. Let's actually just visualize this. So down here, this main function, oh shit, I'm not recording, am I? Oh yeah, I am, cool. All right, let's execute it. So the main function is invoked down here. It starts executing. The next function that is ran is this console.log main starting. And then the console.log executes and then returns right away. So console.log main starting is done right away. So that gets removed from the stack. What function should be put on the call stack next?
Second.
Great. Okay. Now which one should be put on?
Console.log second starting.
So the second starting. Okay. Now what's okay, so the second starting should be removed because it's done executing. And the third one gets put on the call stack. In the meantime, second and main are still executing. That code is still being ran. Like it hasn't finished being ran yet. It hasn't returned anything yet. And then third, console.log starting. Third gets removed, or the console.log gets removed, or third starting, and then the third function returns. So that one should be removed from the stack. So in this entire time, main has not finished executing. It is still executing. And then second, and then finally, when second is done, then it returns main. Does anybody have any questions about what the call stack is from like a visualization standpoint? So, but what the reason why this is, so I'm going to go back, is prevalent with regard to recursion is because recursion is a function that calls essentially another function, which it's going to call itself. We'll get into that more specifically. So a function that calls a function that calls a function, all these functions call another function. Let's look at the stack in Chrome Dev Tools. This is where it gets fun. Let's look at CD. Oh, hold on a second. So I'm going to open up a file. Let's see if this is going to work. All right, cool. Ugh. What the hell is going on? I'm going to exit out of there. So I have this index HTML file. I'm going to open up this up in the browser. You don't need to really know much about this right now. So what I just opened up is dev tools, the developer tools. And in here, so I've got this index.html file, and I imported this app.js file. And this is essentially the same code that we just saw. First, second, or start, second, third. And then when I open up the index.html file, it automatically executes the code in app.js. So if we look here in the console down here, it says live reload enabled. Okay, that's regard to VS Code, but it says main starting, second starting, third starting, remove, third removed. But look over here, we also have something called the call stack. So what's great about Chrome and other web browsers is that we can actually visualize the call stack happening in real time. So I'm going to create a breakpoint right here, which is essentially going to say run the code and stop right there. And let's see if it works. So if I refresh this, hope it works. Okay. I'm going to reload this. Source. So right here, it hits this start. It throws in anonymous. So every time you run a file, it's always going to throw like a main, essentially a main function onto the stack. That's just like a default called main. I'm going to step through this entire method and watch it. So the start got put on the call stack up here. The next one is this console.log. I'm going to step through. The console.log got executed. The second got put on the stack. Now I'm going to console.log is the next function to run. Comes down here, second starting. That was executed. The next is the third one. Right here, third got put on the stack. execute, third starting. Now, what should happen next? Third removed from this call stack, but it's not returned yet, so I'm going to actually return it. And third got removed. Now it's up here in the second. Then after I execute this code, second one removed from the call stack. Click it again. There, it's done. It's actually finally returned. Now I'm up here at the start. It's going to return main removed from the call stack. Main removed from the call stack. But now finally it's actually going to return. And we're done. We removed everything from the call stack. Should probably just remove all these console logs. Be a little bit better. Or every time this thing gets returned, might be easier to visualize, but I don't think it's gonna. Let's see how it's. All right, there we go. So I'm gonna refresh this again. Great. Anonymous. That's all. That's always going to be put on the call stack first. I'm gonna step through. Start console log. Main starting. Next one, second gets put on the call stack. Second starting. Third's going to get put on the call stack. Third starting. Then return third removed. So it's not console logging anything because we're not actually console logging. We're just returning a string. Third removed. Second removed. And then start is removed. That's what the call stack. And see how this thing is still loading? It's because this code is still executing right now because I'm pausing at each and every function. So it's still actually executing in the browser. And then I can click one more and it should be almost done. Go on. Okay. That's the call stack. Why is that important? Let's get into actual recursion. Main recursion examples. So I'll create a thing called make directory called recursion. Recursion.js. What? Touch recursion. I'm going to open up this touch.js file. So recursion, there are two things. There's essentially two things you need to know about recursion. You need a base case, and you need to define the recursive case, essentially when the function should call itself. So recursion is a function that returns itself over and over and over again until a base case is hit. So step one, define a base case. At what point should your code stop executing? So when should the function stop calling itself? Step two is define the recursive case. When should the function call itself? Let's walk through some examples. Function, let's do let space x countdown. You guys ever watch the SpaceX videos? No? Awesome. Sorry.
Which explosion are you referring to?
All right. So SpaceX function takes in a number and it will count down to countdown. Takes in a parameter, an argument number, and it will count down from that number to 0. And then it will say take off. That's what we want. So count down from num and return take off when what? When num equals 0. So there's a couple ways to do this. Let's do this iteratively first. What should we do? let count down equal number. How do we do this iteratively?
While
Okay. While num is greater than 0, console log the number, num, and then count down minus minus. Let's try this. Space X countdown, let's do 10. Down here in the terminal, I'm going to execute this. So ideally, value is never used. Let's see it. Oh, let's see if what happens. Let's do node recursion. Uh-oh. Why does it do that? Console log num.
Because you console log a num and not.
Countdown.
Num
Num
equal
is
countdown
the
instead of countdown equal num.
Or while countdown is greater.
Right.
There we go. Great. So this should work. Countdown. I'm going to clear this. I'm going to run it. All right, 5, 4, 3, 2, 1. Great. Now F at the very end should return our console log takeoff. Clear down here. Cool. Works. So we did this iteratively. But with recursion, we're learning recursion. We want a function that calls itself until the base case is hit. So what's the base case for this? So when should the function stop calling itself? Base case, countdown, when countdown, what is it, equals 0? Equals 0. Recursive case, just when, what is a recursive case? Just essentially when the countdown is greater. Countdown is greater. Okay. Let's do this recursively. So countdown, start from scratch. So what's the base case again? If so when countdown equals 0, if countdown, so we get declare a let countdown equal num. When countdown equals 0, what do we want? Console.log or return takeoff, but takeoff. Else, what do we want to do? Don't really need. You can do space X countdown. What do we pass in now? Decrement? How do we do that? num minus 1. So let's console log num. So in here, or countdown. We need countdown down in this. Do we even need a variable countdown? So let's delete this. So when num equals 0, num. Taking a number, if num equals 0, console log takeoff. We can actually move this to the top. No, we can't, because. So if num equals 0, return takeoff. Else, we're going to return. We're going to return the function itself again, but pass in num minus 1. So if we pass in 10 here, it's going to come down here. Is 10 greater equal 0? Is 10 equal 0? Nope. So it's going to come down here. It's going to console log 10, and then it's going to return space x countdown 10 minus 1, which is 9. So next, it's going to come back up here, countdown 9, come down here, console log 9. Think of it as, who has seen Inception? Yep. Remember, it's like a dream within a dream within a dream. And the very first dream does not end until the person wakes up from the like third deep layer dream. So the dream within a dream, and you get woken up, you're still in a dream. You get woken up again, you're still in a dream, and then finally you wake up, and then you're actually in the dream. So that's where this recursion comes in. The first SpaceX function, the first time it's called, it's still executing. So it's a first layer or first level, and then calls this second level deep, comes up here, passes in 9 down here, returns SpaceX countdown with 8 in there, so it's like another level deep, so it's like 10 levels deep. Let's execute this code and see what happens. Hopefully it all works. Clear. Oh no, what happened? Is it equal? So this is, you'll see maximum call stack exceeded. That's what's bad. We don't want that to happen. That's why we need a base case. So what happened? I don't know. Console log num. Ah. So num is greater than or equal to, or just try it again. Still gonna do it.
Because you're returning SpaceX countdown regardless.
Ah.
Even if base case is
Okay. So what happened was I wasn't once it came into here, it wasn't returning anything. It was just console logging. Then it would jump down here and return this. If I return console log, that's when you want to. That's when it's actually the function's going to end. So I'm going to clear this. Good. So you always need to return. There we go. So a function, so there's two things you need to do when you're declaring a function using recursion. First, declare a base case. Once you declare a base case, then pretty much every other thing, you'll return the function itself. What's another, let's do another one. We can do it adding. I'm going to take in a number. I'm going to add every single number up into the argument, the number I pass in as an argument. Let add up to, takes in a number, and then what's my base case?
In best case, the number that would be number.
Number what?
Whatever number you put into the function.
So I'm going to be adding, so if I take in 5, it's going to do 5 plus 4 plus 3 plus 2 plus 1 plus, so I'm going to add everything up together until, right. Okay. So what's my base case? When do I want it to, so I want to add number up to, once it hits 1, I essentially want it to stop adding up to it. So my base case, if num equals 1, if this input equals 1, then I just want to return. What do I want to return? 1, or 1, right? If num equals 1, return 1. Else, essentially return, what do I want to return? 5. So I've got 5. I want to return plus, so recursion, it's a function that's calling itself. So return add up to num minus 1. See what that, add up to 10, let's do 5. Clear. All right, since I didn't, I can console log this. It really won't work that way. Does this work? There we go. So let's console log. Num. So what should num be each and every time? Like what's the value of num? It should just kind of be, yeah, 5, 4, 3, 2, and then it returns 1, so then 1 gets added. Recursion is a little, takes a while to get to grasp it. So
the big difference is we're putting everything in functions now, right?
you've been putting things into functions. So yeah, yeah. So the SpaceX, let's go back to here. It's a little easier to comprehend, I think. A recursive function is a function that returns itself with a different input value. So the first input value is 9 or 10, then the next time it calls itself, it's going to be 9. And then, so it comes up here, 9, it's input in there, it comes back down here, it calls itself 9 minus 1, 8. So it calls itself again with an 8 input into here. Comes down here, calls itself again with 7 put in it as the input value. Just keeps doing this until the num equals 0. And then it comes into here, which is the base case, and it returns, like stops executing. And then the whole stack of code stops executing. So if I didn't, like before I didn't have this return statement in here, we received that error. Bam. So I was like, hey, it looks like you're in a recursive thing. Your maximum call stack size exceeded. So it built itself up all the way up, and it just breaks.
You can also call that stack overflow.
Yep.
Where it looks like it's
Yeah. So you always have to ensure that you return in your base case. So let's go through the challenges today. We have recursion. So you've already done all these challenges: factorial, palindrome, 99 models, Roman numerals. Some of you even already completed them using recursion just by happenstance. But today, you're going to go through and complete all the challenges again: factorial, palindrome, 99. The logic is all pretty much there. But now you got to go back and do them utilizing recursion. Yeah, I don't think your test cases should change. Let's do the first one together, factorial. So what's the base case of factorial? We kind of already won. All right? Yep. So base case, when input equals 1, return 1. And then the recursive case is just like anything else. Yeah, you don't even
Also for 2, would be the 1 as well.
for 2. So any other case, it essentially just whenever, yeah, just always ensure you define the base case, and then pretty much the next thing is just you return, function with input value minus 1. We already kind of did it, not in SpaceX, the other to add up to. So let factorial equal num and if num equals 1, return 1, else return num plus times factorial num minus 1. So what is factorial 5? Console log. I'm going to console log here, console num, just to see the countdown. Node, recursion, just. All right. So the first input, factorial 5. 5 gets input into the number. If number equals 1, return 1. It doesn't equal 5, or it doesn't equal 1. Comes down here. Return 5 times factorial 4. So 4 comes in here. 4 does not equal 1. Return number, which is 4 times num minus 1. So 3. 3 comes in here. 3 does not equal 1. 3 times 2 essentially comes up here, and 2 times, well, then it comes in here and returns 1. So this would be 1. So it's like 5 times 4 times 3 times 2, and then times 1. Num equals 1 at that point. And you get factorial, and then you get 1 point. There's other ways to do recursion like this. It doesn't have to, it can be, you can like, there's just other ways you can return a function that calls itself. But this is one way to do it.
What's the big advantage of this method?
don't know if there is a big advantage. You rarely, if ever, see it in actual applications. I haven't seen one in my last job. Have you?
No, like, it's less useful.
Right.
It's very common to see recursion problems in coding interviews.
Yeah. One of my coding interviews actually to get into the program that I graduated from, like, I had to do something, I did it iteratively, and then they're like, hey, do it in recursion. Luckily, I learned recursion, but I still didn't quite understand it. I just kind of understood that, oh, okay, there's a base case, and I have to return a function I called itself. And I did it, and I was like, oh, okay, it worked. But, and it took me a while to actually, for everything to sink in. It's like, oh, okay, I understand.
Recursion both helps when you have divided numbers, right? So,
Yeah.
like, sorting numbers.
Mm-hmm. Yeah. So, saying that, binary search.
Thanks, Beck.
There you go.
Thank you for the reminder. Binary search is a really, we're going to cover it, we're going to try to cover it actually just in our putting together some curriculum that covers data structure specifically. And you'll see it again there. But. So binary search. So as Beck said, searching algorithms, let's bring some up. YouTube. It's all about efficiency when searching through stuff. So sorting algorithms, visualize.
Right, yeah.
Don't be a commercial. No.
Whoa.
Okay, so this is where recursion could be an advantage, and as well as like binary search. You like this one?
Yeah.
So this is a sorting algorithm. What is going on? Why is it taking so long? These are different sorting algorithms that are written, and how they're implemented depends on how fast items can be sorted. So you've got an array of random integers between 1 and 100, and you need to sort them in all, like from 0 to 100 in a sequential order. There's efficient ways to do them and inefficient ways to do them. I think if you look at like a company like Uber that has so many data points and everything like that, and they need to like search through a database for a very specific thing, and they use just like I don't even know what's a horrible bubble sort. Bubble sort's a horrible one, but yeah, here are the different sorting algorithms. Visualize, selection sort, and this is how fast it takes to sort them. So bubble sort is right here. It's really slow. Bubble sort's down here. It's really slow. All these sorting algorithms are already solved. Yeah, it's still going. I think this does have.
All videos wasted without sound.
Yeah. Anyway, but so there's sorting algorithms, and then there's searching algorithms. Binary search is a pretty efficient way. So think of it like an array again. You need to find one element in the array. You can do it iteratively. Look at the first index, look at the second index, but what if the answer, what if what you're looking for is at the very end of the array? So if the array is like 100,000, a length of 100,000, it has to do that, look through 100,000 things. Binary search is a way to break that problem down and like do it efficiently, so some much smaller steps. So let's do what binary search does. I'm not going to actually code, I'm just going to pseudocode. So binary search takes in an array. What am I doing? I have an array somewhere that's easily accessible. Jesus. let array equal these 5, 4, 9, whatever, that's good. 10. So the way binary search works, you want to break this problem down. It uses recursion to solve. So if I wanted to find 10, let's do 9. The way binary search works is you want to break this array into 2 arrays. You're going to cut it in half. 65 to 6, 8, and then what is a 4? And then the second array right there. And then it checks to see if the middle, so what's the middle element of this? It'd be like, let's say 4. So it breaks it off, and then you actually want to break this one out into 2. Break this one off into 2. And just keep breaking it down until you actually find the base case where your input value that you're looking for equals one of these. Here. Find data. Sure. So, and this is done recursively, so you pass in the first array into the binary search algorithm, and then if like the middle break it off, cut it in half. If where you cut it in half, that value does not equal what you're looking for, call itself again, but pass in 1/2 of the array. And then it essentially calls itself with this as the input. And then splits it in half. If the middle portion of the array right here does not equal what you want, cut it in half again and input this part, this second, or like this first array into the binary search algorithm. It just keeps on calling itself until you end up finding what you're looking for.
Excuse me, Tom.
Yep.
Do the arrays have to be sorted in order first before binary search works?
No.
All right.
Nope. And the whole point is you don't do array.sort and then look for it. So that's where you get into a binary search tree. In that case, yeah. So that's the second part. And it is a difficult problem because it's using recursion and you're calling itself a lot of times in multiple parts of the program or multiple parts of the algorithm. And you can binary. You can there's plenty of examples of binary search. So if you want a visualization of that, highly recommend Googling it. See how the binary search algorithm works. With that, I'm going to stop recording.